Thank you. Hi, I'm Martin Dangerfield. I work for Cake Solutions. We're really proud to sponsor tonight's meetup, so because of that, it means I get to talk in front of you. As you will see, Carl works for Cake. Also, Alex at the back. Alex, wave. Vicky next to him. There we go. The real plug is that we're hiring. We're hiring Scala developers. We're hiring DevOps. Hard plug over. If you want to talk about a role in the UK, come and find me. Come and find one of the guys. Failing that, I'm going to pass you over to Carl. He's going to talk to you about some very interesting things. And have a good evening. Thank you.
Thank you. Okay, so I thought it'd be good to start off by talking a bit about why I and Cake in general are interested in doing some chaos engineering and runtime monitoring of distributed systems. Traditionally, as an industry, we've been quite good at focusing on proving out that systems can scale. One of the things we've often failed to do is prove that those systems are resilient. And we've also sometimes perhaps been a little negligent by what we mean by proof. So I'd like to try and examine some of those things today. So let's start by looking at what chaos engineering is. So chaos engineering emphasizes an empirical approach to testing and monitoring your distributed system. So we're interested in performing direct observation of that system and then inferring things about it. A typical chaos type experiment, well, you start off by defining a view of the system. That might be by defining a set of business or system metrics you're interested in observing. You're trying to keep those metrics within a certain set of boundaries, be they static boundaries or dynamic boundaries, dynamic changing over time. Then, having defined your view of the system, what you then want to do is randomly inject faults into that system. And as you get more sophisticated at doing this, it might not just be random. You might constrain that randomness in some way because you've got some additional knowledge about what you can and can't do. So examples of injecting faults might be simple things like just simply killing the containers, like you might get with Chaos Monkey. Might be changing network behavior by dropping packets, reordering them, bit flipping. It could be even something as taking a Linux system call and with a certain probability ensuring it returns an error code, which can really mess things up, as we might see. It's actually a typical chaos experiment. And the idea then is you perform that experiment and by making observations of the system that you're putting under this type of stress, when you start to see deviations from your expected or steady state behavior, you can then start inferring weaknesses about that system. Yeah? Weakness here meaning perhaps a fault or some sort of aspect of resiliency you should have programmed for but didn't. So that's what chaos engineering is. Now, before I get into the meat of this talk and examine a particular framework for supporting chaos engineering, what I thought would be a good idea is to go through a little thought experiment. And imagine, as we'll see in a moment, a type of ideal world. Oh, by the way, yeah, chaos engineering. You may well want to apply it to production systems as well, for reasons which become evident as we go along. You can't always, by the way, apply it to production systems. It might be too costly to the business. So let's start off with a goal. What's my ultimate goal here? My ultimate goal is to just simply verify the correctness of a distributed system. Yeah? to some level of verification. And traditionally, we've got three standard approaches to this problem. Testing, so we might have unit, integration testing, system testing, A/B testing, whatever. And that'll give us some level of confidence. And then we have things like static analysis, where you'll under or over approximate the thing you're observing. You'll build models which over or under approximate that thing. And you might build those models by using abstract interpretation or perhaps using some other manual magical process. And then right at the bottom, we've got our gold standard, where we go away, we'll build up a full-blown mathematical model of the system, and then go away and prove all sorts of nice properties of that system. Yeah? So let's imagine for a moment we've succeeded in doing the bottom one. Yeah? That's a really hard task. I've done it. Yeah? So let's imagine for a moment we've built an application. We now feel 100%, or as sure as we can be, that that application is correct. What happens next? Now, you built the application, you proved it correct. What happens next? Well, if that application has any business value, you're going to want to deploy it into some form of production-like system so you can monetize it and get some return on that investment. Let's examine what happens. What might happen? So we might decide to containerize that code in, say, something like Docker. In doing that, we've added in some wrapper code to our application. We've moved our application away from the theoretical model we've proven it correct to. We've added in a layer of doubt. DevOps come along and perform some magic. They'll wrap that code up in provisioning stuff, inject processes into those containers, inject agents into those containers to add in monitoring, metrics, all sorts of other instrumentation that we as developers may not have taken into account. More doubt enters the equation in terms of the correctness of our code. DevOps then decide to deploy this code and orchestrate it within commodity cloud-based hardware. What that means is on the type of PC, by and large, and PC-type kit that you might get off the shelf, which means that as you scale, there is a higher probability of failure. Doesn't matter how good you've written that code, failure is going to occur now with a high degree of certainty. The data center itself will dynamically maintain and relocate your code without your knowledge as it's running, for reasons that only they know. Might be just a case of shifting your code from one rack to another. But that will happen. And then as this code runs, sooner or later, a crisis scenario is going to occur. And that means you're going to get human intervention. So no longer are we worried about software and hardware faults. We've now got humans entering the equation. Software and hardware faults, we're used to trying to test those, tease them out in one way or another. Human processes now come in and kick in. So someone will get some form of PagerDuty call. And that poor so-and-so, at whatever hour of the morning or night it may be, then has to deal with that crisis scenario and fix it under high stress. Yeah. They're going to make errors. Yeah. So now in the situation whereby it's very hard to feel confident that our code, our application is still correct, regardless of how we've built it. So what's happened here? We've taken our application and we've deployed it into a dynamic environment. It was probably only proven against certain types of static environments. It's now running in a dynamic environment. It's worse than that. We have little or no control over that environment. That's not to say that upfront effort is worthless. It's just to say that the game has changed. The deployment is typically using unverified processes. It's not uncommon that your deployment code will be built to a very different quality compared to your development code, your application code. So the potential for an unanticipated failure now is extremely likely. So we've got no choice. We have to embrace and test for failure now. And that's generally what most of this talk is about. It's how do we now do that? How can we systematically do that? So the idea here is I'm going to introduce a toolkit I've been working on for a while. Still under development. It's open source. It's all Scala. And the aim of this toolkit is to try and simplify the process by which we may do this type of resiliency testing. There are other toolkits out there, but they're often a lot harder to use because they're built for a very particular engineering scenario. They're also often very limited in the type of fault injection that they can engage in. And I'll cover a little bit more of that shortly. So the aim of my toolkit is, optionally, I want it to be able to deploy, orchestrate, and instrument some Docker container code. The idea is we'll take production containers, we will not touch them. But what we will do is add extra layers of software on top of them. Yeah? And in doing that, we'll be able to inject code into those containers without changing the core stuff, the stuff that we might normally deploy to a production environment. I would like it to be as agnostic of the deployment environment as possible for the very simple reason that when I write my tests, it doesn't matter whether I'm running those tests, those resiliency tests, in my local dev environment or in a staging environment or a production environment. The same tests, modulo a little configuration magic, should still be able to run and prove out whatever resiliency properties I'm interested in. And then what's absolutely important is good compositionality. So I'm going to have to define some way of measuring and monitoring behaviors of my system or parts of my system. And then having done that, I would like that to be composable because I would like these things to be as reusable as possible. And then we'll get to the stage of let's go away and define some experiments. I'd like these to be quite easily defined, really, quite naturally defined by some developer notion of natural. But I want them to be as reusable as possible. Because often, one project, you'll go away, and it's a set of resiliency testing you'll do there. On another project, it's very similar resiliency testing. There'll be aspects of how you tie those experiments to the system, how you do that binding that'll change, but really, the guts of the experiment will stay the same. Split-braining one network is pretty much the same as split-braining another. All that changes is the network and maybe how you do the fault injection. So that's what we're going to look at. And at the core of this library is the notion of templates. So the idea of a template is it's effectively a library slice, which you go away and you define. And you're defining it because you're going to have this black box, this system. And you need to define how you're going to instrument it. We want to instrument it in two ways. We want to add in sensors there so we can see the radiation from that black box. We also want to have data injection points because we're going to poke it as well. We won't know what's in the black box. Oh, well, I say black box, it'll be sort of grey in the end, but think of it as a black box from now. So we can poke it with the data injection and we can observe sensors. So in order to get that code there, for example, to get that instrumentation in place in the black box, we're going to have to do two things. First of all, our Docker image is going to have additional instrumentation layers. So we'll need to define that. We're going to need to inject some code and resources into this image so we can then run it. But so that we can then define our chaos experiments, we're also going to need to define some library code so we can interact with those instrumentation-specific sensors and instrumentation-specific data injection points. Now, the code for doing this, interacting with that block box, just by its nature, it's going to be side effecting. Yeah, can't escape that. So, because in a sense you're interacting with the real world, side effects will occur. So what I'm going to do is I'm going to keep my main library code as functional as possible. And I'm going to push these side effects and wrap them up using something called extensible effects. And I'm not going to take a deep dive into this at all. I'm just going to show you how to use the library. If you want a deeper dive into how we can define our own effects and what have you, go away and look at the Cake blogs. There's some recent articles there. They take a deep dive. The key library I'm using there is something called F, which is similar to the Haskell extensible effects. It has some pros, it has some cons, but here it's going to work just right for me. Because I want to be able to have lots of freedom as to how I choose and mix my templates. I might want to have network injection in one experiment and JMX censoring in another in the same experiment. But in another experiment, I might want to have a different mix of effects and therefore templating. Now, when we sensors generate events, what we're going to do is we're going to corral those into Monix observables. I need some logical data structure to contain those things and keep them under control, so I've got a common sort of source for observing them. But we won't really see too much of that. That's actually hidden in a lot of the internal library code. I'm just pointing that out to you now. Okay, so let's explore a worked example now. So let's imagine we've got a network. And I'm going to have a left network, a middle network, and a right network. And to that network, I'm going to add in an Akka cluster. It'll have in one container, one Akka node. In another container, another Akka node. This container running an Akka node will connect to the left and middle networks. This container running an Akka node will connect to left and middle networks. And likewise, we'll have two other nodes, A prime and B prime, connecting to middle and right. And the whole point of the middle network is so I can induce faults, for example, down that middle network. And if I do that, you'll notice the left nodes and the right nodes can no longer communicate with each other. And with the right configuration in play, or wrong, depending on whom you are, we'll then be able to split plane the Akka cluster. In order to get to that stage, I'm going to can it so that A will be the leader. So I'll set that up to be the initial seed when we form the cluster. And I'm going to enable a feature of Akka, which is not recommended for production, called auto-downing. So when a node in an Akka cluster becomes non-responsive, the rest of the cluster would normally send that node to being unreachable. What that means is consensus decisions can no longer be made in that cluster. So you can't elect new leaders and things like that. Basically, your cluster is wedged. It becomes a single point of failure. With auto-downing, after a period of time, that unreachable node will be outed. Yeah, leader will force it out. And as a result of which, we suddenly re-establish sanity in a cluster. Hopefully, we've got to get rid of all the unreachable things. So we now have a coherent cluster. Consensus decisions can occur. Okay? So that's what we're going to do. That's the example scenario we're going to build. And I'm going to do that using a bit of Docker Compose. I'm not going to show you much of that. So under the hood, there will be a bit of Docker going on. I'm not going to show you much of that at all. But you'll see it happening in the background in the demo. To a certain degree, we've got to touch on that. So here's some example code. Down at the bottom, we can see here we've got a string version of something that looks very Docker Compose-like, for those of you who've played around with Docker Compose or Fig. You've got a list of your services, and here I'm calling out to a function with a bit of string interpolation, and I'm saying what the name of the node is and what networks it's joining. And down at the bottom, I've got my 3 networks being defined, left, middle, and right. Up at the top, we've got something that looks like standard Docker Compose stuff. Ignore the template section for a moment. We've got the usual stuff where you configure your container using environment variables, exposing certain ports, and we're saying what networks it connects to. This is non-standard. So this is a bit of syntactic sugar. I have to process that and then turn it into real Docker Compose stuff. The key piece here is the image bit. That's our immutable production-ready container. And up here with the resources, you can see I've got 2 package-like paths, and that's telling me about the instrumentation layer code that I'm going to use here. So I want to do some JMX interactions, and I want to play around with networks. Why I want to do JMX interactions will become clear in a moment. But the networking is obvious. You want to split brain, you got to do something with networks. So let's think for a moment what sort of instrumentation we need. I need to see the state of my Akka nodes. I need to see who's in the cluster. I need to see who might be unreachable. And I'm going to do that using the Akka JMX console tools. For those of you who don't know, these tools are now deprecated in favor of a new Akka cluster management layer, which effectively is more REST-based. They've become deprecated because this stuff is still on Google Code, and it's about, oh God, it's about 5 years old or 2 years old or something. It's not been touched in that time. Then, in terms of data injection, I'm going to simulate JVM garbage collection pauses. I'm going to do that by pausing containers. And, excuse me, network loss. I'm going to take this middle network and somehow I'm going to do something to remove it. What I do will end up being interesting. It'll be non-standard. Okay, so we said something about configuration of the environment, how it's set up, the networking and what have you. What I want to do now is start talking about what is a chaos experiment and how I'm going to model it here. And then we'll start looking at what the implementation would look like. And as part and parcel of looking at how the implementation will look like, we'll get to see how runtime monitoring can be catered for. So let's imagine for a moment we've got some notion of a behavior. We've got some way of understanding what a behavior is. Now that behavior is going to have to consume events from some sensors. Yeah? Why? Because it's sitting there observing the black box, looking at the sensors, looking at what that black box is radiating, and when it sees that black box exhibiting the right or the wrong behavior, it's going to do something. So, the moment we successfully detect our event, we've seen the right sequence of events coming out of our sensors, what we're going to do is we're going to change state. So here in a chaos experiment, we can think of state as being a runtime monitor. We're going to change state. And when we change state, we're going to perform an action. And that will be an opportunity to perform some form of data injection. Yeah? You've seen the cluster form. Now do something. See a node has become unreachable. do something. And then, obviously, as you change state, you're going to enter into a new state. You're going to start monitoring for some new behavior. And quite simply, you can see that kind of graphical relationship, you can start chaining those together to form bigger things, bigger graphs. I'm not going to go too much into what fun we can have there. But if you allow your imagination to run wild enough, it's not too hard to imagine, maybe there's some form of dynamic logic there, or a temporal logic, or something like that. So let's see what a chaos experiment for our particular scenario would look like. So, start off, we've got for comprehension. And if this experiment is a success, we're going to accept. F of M here is a monad. And it's going to spit out instances of notify. So instances of notify will either be passes or fails. M itself will either, this defines a stack of monadic traits. So it says what effects I want to have around. And it doesn't commit me to an order of these effects. And so as a result of that, I end up with some nice compositionality here, beyond anything that monadic transformers or free monads can give me, if you know what those things are. If you don't know what those things are, goodness. Yeah? Two key things I want. I want some JMX type stuff, and I want some networking stuff. And I might want some other things around, like to deal with errors and async behavior. But let's not focus on that too much. Let's just worry about the shape of this experiment. So let's assume for a moment we know what a runtime monitor is. So we do some runtime monitoring. Perhaps here we wait for the cluster to be up and stable. It's not enough for the cluster to be up. I have to see that it's up for a period of time, because that's the reality. And then once that happens, I want to do some fault injection. So assuming that's a success, I want to move on. If that's a failure, experiment stops there. If that's a success, I then want to move on, and I'm going to start simulating a JVM garbage collection event. And I'm going to do that by effectively pausing the specific Docker container. So this is just a bit of functional code, which when it runs, we'll have run this side effect in code, which pauses the Docker container. And then we're going to start observing. Now, I don't want to split brain at this point in time. So I'm going to wait until the node I've paused becomes unreachable. The leader sees it as unreachable. And at that moment in time, we're going to recover. Yeah? And end the JVM GC pause. And then we're going to become a new runtime monitor. And here, I want to check the cluster becomes stable again. Yeah? So in other words, the cluster reforms and remains stable for some period of time. And then finally, I actually want to split brain it. I want to bring down my network. And the way I'm going to do this here is on every container attached to the middle network, using TC, I'm going to drop packets with a 100% frequency. Now, the reason I do that, rather than deleting the middle network or whatever, is because if I do that, lib networking has a bug. And 50% of the time my tests do what I expect them to do, and 50% of the time they don't. Whereas if I do that, I get the expected outcome. And then what we're going to do down here, our final runtime observation, we're going to wait until we actually split brain. Right, quick poll. 4 nodes in the cluster. We split brain. How many splits do we get? Do we get 1? Do we get 2? Do we get 3? Do we get 4? So hands up. How many think we get one cluster forming? How many think we get 2 clusters forming? How many think 3? How many think 4? And the rest are sitting on the fence. Well, we'll see in a moment. Don't take my word for it. Do the experiment. So let's go away now and look at runtime monitors. Here is an example of a runtime monitor. And it's quite a complex one, which is why I thought I'd show it you. So we're taking in a series of addresses, which are going to be the nodes. I expect these nodes to be in the cluster. Now, runtime monitors are, for all intents and purposes, nothing more than state machines. So if the state machines, you need to say what the type state is. There it is there, Boolean. And we need an initial state. We'll start off in false. Yeah? When I'm in the false state, I'm going to do something. I'm going to look for something on my sensors. When I'm in the true state, I'm going to look for something else on my sensors. Now, I must monitor events from a sensor. So again, needs to have a type. Here, we can imagine that this is basically a case class, and it's containing information about who is unreachable, what members are in the cluster, who's the leader, stuff like that. That's the sort of goodness you might get if you've ever used JMX, the ACA JMX console command line tool, or whatever we choose to call it. So when we're in the false state, we'll make an observation, hopefully. We'll see this event. We'll look at the members part and the unreachable part. If unreachable is empty, yeah, no one's partially out of the cluster, got in and partially dropped out. And all this bit here says is every member of that nodes must be a subset of the up members that we observe. When that happens, we know that everything up there is currently up and reachable. In that scenario, and only that scenario, we're going to go into the true state. We've made our initial observation, a cluster appears up. But we're going to go into this state, and we're going to stay there for some period of time, 3 seconds. When we're in this true state, we're going to keep monitoring unreachable and members. If we see anything become unreachable, we're going to fail. If we see any of our nodes up there cease to be up, we're going to fail. If, after this period of time, we see a state timeout, we know we've not seen anything negative for that period of time, so we're going to pass. That's our runtime monitor. Now, there's one other runtime monitor around, which is unreachable. I'm not going to bother defining it, because it's a little bit easier than that one. So let's see. Oh, yeah, that bit. So let's see now how adding that information into the original experiment changes things. So we know what the actions are going to be. Let's look at what the runtime monitors are going to be. So the first thing is I must see these 4 nodes, A, B, A prime, B prime, being in an up state. Yeah. Then the next thing is, after that, I'm going to do the JC pause. I must see right A become unreachable. Then I must see these 4 things being in the cluster again. It stabilizes. Then we're going to do the network partition. And the answer is you get 3 clusters forming as a result of this network partitioning with auto-downing in effect. A and B on the left side will remain a coherent partition. A prime on the right side will form its own partition. No one wants to speak to me, so I'll carry on speaking to myself. And likewise, B prime on the right side will form its own partition. And then just quickly showing you how to run it. So up until now, in effect, all this is just some syntactic, it's just really an enriched DSL. When I come to run it, I need to bind that left A symbol, which is nothing more than an identifier up till now, to a real node in a cluster. And that's what's going on there. That likewise will actually be binding the middle string to a real network in our cluster. So, if I've got that right, yeah. Let's quickly show you a demo. And I'm hoping this works. And you will need this to be larger. Absolutely no idea how long this will take. But it should work. So what will probably happen is we're going to start using JMX, probing the cluster before the cluster is formed. So we should see an error. And then when we next reprobe, the cluster will have formed. Bang. We can start monitoring. So this is just some compiling stuff. There's a bit of layering of containers it has to do in the background. And that's in effect what's going on at this moment in time. If I was monitoring the Docker events stream, we could actually see it building these things in the background. But I'm not imaginative to do that sort of thing. And the moment of truth should happen in a moment. Now, if it comes up with a whole load of red, that basically means that Docker Docker has got very upset over the change of network. I restarted Docker machine to avoid that problem, but we'll see if that manifests or not. And you can see there on the network graph, just down there, something's happened over the network. And I don't recall telling it to download anything hooky. Not tonight, anyway. Oh, still doing something. Oh. Well, I can assure you it works on my laptop. And it was... was that something there? Yeah, right, okay. So, as I said, the first thing we'll see is an error. That's just simply saying, I've tried to probe the cluster. It wasn't there. Until the cluster comes up, the JMX command line tools won't work. We're now getting a false and a true there. Cluster was measured stable. We've gone in to do the GC pause. We've seen unreachable. We're then recovered. And now we're getting into the stage where we're actually going to split brain the cluster. Bang, a whole load of state stuff is matched. Bang, we're there. There you go. Split brain the cluster. And proved it in real time. If you want to play around with that code, it's available. Let's just quickly finish off. So I've applied these techniques to quite a large range of fault-inducing scenarios. All the scenarios have one weakness at the moment. They kind of make a closed world assumption. But you know, I've got stuff in there playing around with libFRU, stuff demonstrating that real latency and packet drops and things like that and reordering can occur. So a lot of goodness there. There's a few next steps which we'll just quickly finish off with. The next stage, which we're quite far into actually, is proving this library out on a range of real-world examples. So we can actually start doing real KS monkey type things. So we can start taking it to the next step, whereby we're doing some more fuzz-related testing of resiliency. and we're directing that. Directing it by taking different types of models. Some might be based on static analysis. Some might literally be by direct observation of the loggings. Build up the model and use that to work out where your potential injection scenarios are. Yeah. So that's where we're at. There's a series of references. All this material is available, and I'll let the Raphael and what have you at Virtuous Labs know where this is, so they can advertise it to you guys. So thank you. That's the end of my talk.